people there. They actually also have a live chat over there. Sometimes people ask questions and they answer each other. If needed, I can also forward the question from there as well if I can monitor the live stream there. Yeah.
Okay, I'm back.
You were muted when you were talking, so.
Yeah, I'm trying to set up YouTube live, so I have to temporarily mute myself. So Howard, this is something, a decision we made early. When just John Hutchinson and early talks, we were undecided whether we're going to put video online. So then initially we have nearly 2,000 people. I guess John Rogers went beyond 2,000 people.
That's amazing.
And we said to people, we actually believe in history, the quality in long time. We're going to put every video on the same day online. Then live attendance drastically dropped. I think now it's stabilized to 200 or 300 level. So it's almost like TV show, more live audience, but many people just watch on replay.
Yeah, the replay over the time, actually, there were thousands of views there, and it's available in multiple platforms as well.
How do you find it? You go to YouTube and then like EML or something?
Yeah, I'll send you the link. We have a channel there. Yeah, all the previous videos, you can actually watch all of them.
So how do you start to do this?
It's one of our slides.
Okay, good slide. Okay. So, Howard, so at this section, usually the discussion leader interview the speaker. Now you're the discussion leader.
I'm the discussion leader. I see.
So basically, we get people familiarized with the speakers. You still need to do a formal introduction at 10 o'clock, in your case, 9:30. Spend a few minutes, introduce your co-speakers and yourself.
Yeah, that one of our slides, we have a very brief introduction of who we are. But I mean, for you and Tang and anyone listening, we can say that, Manouk was a postdoc with me at Harvard in early 2000, I think. Yeah. Oh, look, he's wearing his T-shirt, whereas I'm
in honor of Harvard. So I was like, I have to put it. Come on.
Yeah. And I'm thinking about the French, right?
Yeah, I saw the Lafayette.
And what Manouk will tell you a short story was he was planning to spend a 4-month sabbatical in Princeton with my research group to do some small scale hydrodynamics, blood flow, or some other colloidal problems. And he arrived around March 1st, and the university closed about a week later. All labs got shut. And so he was at home, and, we were both reading, and one thing led to another. We got very interested early on, already in March, of this question of asymptomatic transmission. And then, one thing led to another, and we decided we needed simulations, and a couple of people from my group tried to help, but Manouk knew Simone, who's an expert on numerical simulations of a different kind. And then they, along with a couple of people from my group, have put together a set of studies that have now led to 2 published papers as of a week ago, and 1 paper under review, all on this theme of what would it mean if you're just doing casual things without a mask, speaking, maybe exercising, maybe something else, and what might that mean with respect to spread of a virus that's airborne at the scale of you and a colleague.
So actually, Howard, you are the only fluid mechanician given an EML webinar. So I guess this goes back to a general question to you specifically. So you and I have neighboring offices before. we all regretted that we did not spend a lot of time to talk about solid mechanics and fluid mechanics, just learn from each other. We both express that regret. Of course, in United States, at least, solid mechanics and fluid mechanics separated because of conferences are separated. So if EML want to do a little bit more fluid mechanics, you have any suggestion? Is this still worthwhile?
Well, I guess it depends. So I, as you know, and you just said it, I very much regret certain things when I was younger about not learning more about mechanics more broadly, especially when, you know, my first lunch was, you know, with Bernie Budiansky and John and Jim and, you know, others. And I you know, regret not really learning over many years. And I should have just spent a few months at least trying to learn some basics and on the elasticity side of the world. But I don't think of this sort of as a, I guess what we're going to tell you is a fluid mechanics problem. But what we're really going to tell you, I think, is there's an issue that's come up in everyday life that has changed the way we live, which we have spent time thinking about. What does it mean for an airborne spread of a pathogen? And what do very basic mechanics ideas say about that, whether it's using an experiment or doing a simulation, just to learn about that, because we weren't doing this professionally, but we do think we've learned some things that are worth sharing, and they raise some other questions. And I think if you want the fluid mechanics person, you know, there is this intersection of elastocapillarity now in mechanics where people are thinking about surface tension and elasticity and a little bit flow, you know, and those are sort of beautiful mechanics problems, you know. I don't think the good Lord ever drew a line down the middle and said fluids people to the left, solids people to the right. That was an unfortunate intellectual divide, and it's hard to bridge because of our educational approach. But there are some research groups trying to work across it. You know, Dominic Vella would be an interesting person to have talk. P.T. Brunn would be, he's my colleague at Princeton, would be an interesting person to have talk. Some of the Europeans, Jaco Snoyer would be, Jens Eggers, who, there are people I know who are working at this boundary of fluids and solids. Just find an interesting talk.
Terrific. I'll send you an email to ask you for names. Yeah, actually, next week's webinar will be unusual. It is a lady from China. She studied for many decades of sandstorm.
Studied what?
Sandstorm.
Sandstorms.
In China, Western China. She stationed in big testing facilities. She herself, I think, early on, trained and solid mechanical. Theoretical side, but now she's so broad.
Yeah, no, I mean, I think something a lot of us have in common, we might phrase it different ways, is that, you know, we probably all wish we knew more about mechanics as a very broad subject and all the things it touches on, but the style of thinking in mechanics is one we want to share with many people.
Yeah.
And I think the more we can do that, the better.
Yeah.
But I think you and your colleagues for setting something like this up and your iMechanica, Zhigang, I mean, it's amazing. It's just, there's a finite number of hours in the day, and I think many of us just already feel overwhelmed.
Yeah, I know.
Yeah, so actually last year, 2019, I had the privilege to present a talk on Mechanica at the National Committee of Theoretical and Applied Mechanics. We did have many fluid mechanics people there. Beverly McKeon was actually the vice chair of the committee, and Gareth McKinley at MIT. So they actually expressed a strong interest to either develop something similar to iMechanica, or actually suggest that iMechanica is actually open for everyone.
Yeah,
so
why not?
Why not? We didn't call it solid
iMechanica. Don't start something new. I mean, that's like another new journal. Who needs that?
Yeah, so it's for example, one thing.
Is this being recorded? I better be careful.
It's a recording.
It is.
It is recorded.
So Howard, so check your enthusiasm for your jokes. That's recorded permanently.
That wasn't a joke, actually. That was pretty serious, I think, what I said.
So Howard, so another thing. So actually, I suggested at the annual meeting last year was we run this monthly journal club on iMechanica. It gains a lot of readership if the discussion leader there, because it stick to the top of the list for a month. Papers and discussions have been read by tens of thousands times, and it'll be very nice if fluid mechanics people can share the cutting edge research or some interesting problems there, and this is a way that we can get people aware of this platform, and then probably can do something together. Yeah, that's one thing I suggested.
Yeah. Also, recently, I've been in recent months, I've been experimenting Twitter. You guys will laugh, but it's a really powerful way to communicate. You guys laugh, I know that. Howard, you should give it a try.
I'm not laughing. I should give it a try. Twitter?
Yeah.
Oh, no.
But
I'll send.
What do you tweet on your Twitter?
Oh, I'll send you guys. I think it's effective because this year is 100 years of Griffith's paper on fracture. So I've been tweeting theme on what I call 100 years of toughness. So each tweet, I explain one classical paper. I hope eventually I'm going to write up as a review.
But the tweets only are allowed a certain number of words?
Yeah, it's extremely effective. So it allowed.
Can you send me the link?
Yeah, 280 words. You know that with David Weiss, you know this, right? Each paper can be explained, important paper can be explained in 1 or 2 sentences. Just find these 2 sentences. And then Twitter allow you to, of course, make a link. You can link to that paper and also allow you to post several figures. I normally select 1 figure. So if one paper cannot be summarized in 1 or 2 sentences and 1 figure, the paper has something wrong. Do you agree? So it's actually very effective. And then people give me suggestions. The other way I use it, actually, Howard, you will enjoy it. I teach fracture mechanics. I want students to run some experiments at home. So one day I start to tear this grocery bag. It's a polyethylene bag, just every grocery shop, the bag is a little different. I tested a few, but they are all anisotropic. Tearing vertical is very easy, but tearing horizontal, very difficult. I just discovered by manipulating it. Of course, people in polymer would know it. So I post my videos and people give me suggestions. We learned this in class, but then they never did experiments in class. It's a dramatic difference. You just pull out a shopping bag, tear vertically, horizontally. So, and then I made a homework problem. Ask each student to present a sequence of videos of their own experiments. And this is on now. It's just beautiful. Students, of course, do much better job than I do. Very creative. So Twitter is very powerful. It almost like a publication now. You post it, everybody can see it. Not only your followers, everybody can follow you and everybody can see it. It's a publication. And
I certainly appreciate how your reach is extended. I've just struggled for myself of trying to prioritize how I use time, and I just haven't been able to sort of factor that one in yet.
Yeah, that's true. That's really true. For example, Gareth is on Twitter as well. He tweets about 1 or 2 tweets per month. Very good tweet.
Okay, I'm going to have to learn how to become part of the 21st century. So,
No, Howard, is not 21st century. Is you have to be younger than 20 years old in order
but I
to do
feel younger than 20 years old. I just know physically I'm not younger than 20 years old.
Yeah. Twitter has all the features. When Turner and I started iMechanica, we were not software engineers. We just used a open source software. We imagined if we could have this, it'd be good. We know how people interact in our field, but we couldn't make that happen. But Twitter has all these features built in. Very powerful.
Do you find that when that many people write to you directly, or they're just interacting through Twitter?
Interacting with through Twitter. I seldom, very rarely receive any personal direct mail.
So people respond. So the Twitter then has their exchanges there, but you don't have to monitor it or respond, or you can just read and learn.
Right. People do not expect you to respond. So this is actually it's a much natural way to correspond to each other than email. Email, people kind of expect you to respond. I'm so behind emails. I just think it's just not the right thing to do. It's a waste of my time.
Well, we have to say thank you for letting, because you brought this up, letting 3 fluid mechanicians in some form or another join your seminar for the week. And we hope people find it interesting to think about.
The topic, Howard Stone. So the editors all know Howard Stone. If Howard Stone wants to say something, it doesn't matter what he wants to say. Just say it.
That's not, I'm not sure about that, but Manouk and Simone have a lot of interesting things to say. I'm not sure I have much interesting to say, but we'll see.
By the way, Howard, you've worked on many different things. All of them very interesting, excellent work. How do you choose a topic?
I have a lot of wonderful collaborators, and some of this happens sort of organically. Some of it happens because of emails I get and respond to. Some of it happens because I think I find, and I think I have a few colleagues, I know Manouk quite well, and Simone might be this way too. I tend to find problems more interesting than any specific area. I tend to like puzzles. I tend to like open questions. I discovered this as late in my research career, not so early in my research career, but I've just found that I like unanswered problems, or kind of what seem like puzzles or things, more interesting than any specific problem in fluid mechanics or mechanics in general. Anyway, so, and I have wonderful collaborators, right, who are tenacious and bring different skill sets. And I think that's just so valuable when you're working on problems, to bring different skill sets to bear on one question.
One technical thing. Howard, you said you have to leave at 11 o'clock, right?
Well, I'd prefer to leave at about 10:45 or 10:50 because I have to do a few electronic things to set my class up.
Yeah, please do that. But typically discussions, this webinar discussion goes on for two plus hours.
Simone and Manouk can take over. They're the experts.
Yeah. So who will follow you as a discussion leader afterwards? Simone or?
Do I have to assign someone, or it just happens?
Right now, all 3 of you are co-host, but there's a technical thing. You need to keep your chat box open. Have you found your chat box? so we can
Yes.
communicate with you. Keep it
Okay.
open.
So I have that open, but when I leave, I can just say leave and it won't affect anyone else?
Correct. You just
Perfect.
leave.
Okay, so
Yeah.
I'll leave around 10:45 East
Okay.
Coast time.
Yeah. Yeah.
And we're probably going to talk for 50 minutes to 60 minutes, something like that.
Yeah. Yeah. Yeah.
And we can follow the chat in case there are questions in the chat. But
Terrific. So we'll start at 9:30. We normally start on time.
yeah,
So when we start, you begin to introduce the talk and your speaker. You're the discussion leader.
I see.
Yeah.
Okay.
So afterwards, two of you. So Manouk, can you be discussion leader?
Yeah, I am here until at least 5:30. So I left already 2 hours free in my schedule, and then I'll see. But normally, I'm waiting a message from my wife. So then, if there is any emergency, then I leave. But otherwise, no, I'll be there.
Terrific. Terrific. Yeah. All right. So, okay, go ahead. Jimmy, you have another question?
No, I just want to say thank you, Howard, for bringing in Manouk and Simon. This is exciting, you know. We have a show.
Yeah.
I do have a question for the three fluid mechanicians. So, like Zhigang mentioned, he's running this 100 years of toughness on Twitter. So one of the questions or a couple questions he was raising over there was, for solid mechanics, fracture mechanics is one of the topic that seems that it's hard to tackle, and also it's not that easy subject to learn for the student. And also the scientific research on fracture mechanics, even though it's 100 years, it's still a lot of unsolved problems over there. For fluid mechanics, my impression long time ago is that the similar thing for the turbulence, or is that still the case? I'm asking the experts here.
So you start, Howard.
I mean, intellectually, I'm sure it's true that there are many interesting, challenging problems about turbulence, but I would argue that fluid mechanics in general has many other subjects about it that are important and pose new problems, some inspired by materials, some inspired by health, some inspired by disease, some inspired by other applications where flow happens, whether it's in a device or in a diagnostic setup or whatever. And there are many now new questions at the smallest scale, the nanoscale, where ions are present and geometries are small. So I think fluid mechanics has many interesting questions. I think it's a little too simplistic to try to say what is the great unsolved problem in fluid mechanics, in the sense that, oh, now we should all go try to solve it.
Yeah.
I think what is getting is more and more obvious is that the type of fluid we are studying are becoming more complex, and therefore the question become more fuzzy, and you need several disciplines often to talk about that problem. For example, with Simon, we study blood flow, and in a sense it's fluid, no? But at the same time it has particles, and Zhigang just talked about these sand storms. Isn't it, again, a fluid that has a very strange structure? So you will ask questions that could look like fluid mechanical. You could also ask questions that are more solid-like mechanical, and you will be in between. And the application will be fantastic if you can understand something about blood flow or sandstorm in different conditions. And you are experimenting that also in pure fracture mechanics, I guess, with all these composite materials, no? Which, though you didn't answer the question, the fundamental question of how really fracture happens, it's even worse now when you tear a piece of paper or plastic, as the example you gave, which gives even a more complex problem to solve. So at the end, we never solve problems. We just multiply them. And thanks to that, it gives different perspective on a large field, no?
Yeah, Howard, can I ask you to share your screen? It's 9:30.
Yeah. Jimmy, there was a question in chat to promote someone to panelist, I think.
We'll do that. we'll do that.
I already answered that question. Yeah.
Okay. Oh no, I see I did something wrong. Okay, can you see my screen?
Yes.
Okay, so good morning, everyone. I'm very happy to be joining the webinar this morning with my colleagues, Manouk Abkarian and Simone Mendez. We're going to tell you about a very timely question that we've been now working on for many months, which relates to a transport problem that we refer to as the fluid dynamics of speech, and try to think about the mechanisms that underlie pathogen transmission, in this case, motivated by thinking about virus transmission in our everyday life. There are many people to thank that have been part of this collaboration, and they're shown on the bottom of this screen, a set of colleagues at Princeton that have worked on this with us. So to start, I thought what we would do is just introduce ourselves briefly, and then we'll each be giving different parts of this talk. So I'm a professor at Princeton. I study fluid mechanics, and I primarily study small scale fluid mechanical systems. Simone?
Yep, so my name is Simone Mendez, and I do simulations in fluid mechanics, and I've been studying blood flows for over 10 years. Then I switched recently to the problem we're talking about today.
And I'm Manouk Abkarian. I'm a director of research at CNRS, and I am a soft matter physicist, we could say, that likes biophysical problems, like, for example, blood flow. But also I like to work indeed in fluid mechanics and small scale flow problems. And this problem was interesting because it was really out of our boundaries, at least for me, and I guess also a little bit for Howard, less maybe for Simon. And we wanted to just, before we introduce more the subject, we wanted to tell you a little bit about how we started all this collaboration and this story. Maybe it can interest you. And so I was basically planning to visit Howard for 2 years now. It was in summer of 2018 when we started to talk and plan my visit to the States at that moment in March of 2020. And when I arrived with my little family to work with Howard on blood flows, 2 weeks later, all the university closed, the school closed, and we started to get depressed. With my wife, we were like trying to put order in our lives, so we started to put the kids in their school at home. And doing so with Howard, we basically spend every day for that month, if you remember, Howard, talking about this problem of spreading, and especially this problem of the asymptomatic spreading. We will tell you what it is exactly. And we basically realized that this could be the heart of the problem that maybe as fluid mechanicists we could try to tackle. And while speaking about that, we were actually saying, oh, but what's the role of speech in all this? And my wife, that is an artist that also had to suffer this confinement, has been studying when she was younger linguistic, and she told us about these features of language is called plosive consonants, and we'll talk about that later. And so from that, since we were confined initially in March, I started to do experiment in my closet, basically looking at these humidifiers and trying to talk in front. So it was very funny. My kids were really having a lot of fun watching me talking in front of this and saying different words like pa, ba, la. And then I even convinced Howard to do some experiments alone in the lab sometimes when there was no one, and you can see him talk in front of a light, trying to disturb a little bit the environment around him. Please. And while we were trying to, we can hear him here. Yeah. Speaking Princeton. And then we contacted Simon to join this problem because we needed, and we realized early on, we will need to do some simulation to basically back up all the experiments we were planning. And Simon was a little surprised initially, we must say, and did a fantastic job that you will see later on.
Okay, so the talk is now organized the following way. As Manouk described, back in March and April, we started to think about this question of asymptomatic transmission from the standpoint of thinking about the flow around you. And so I'm going to have an introduction that just talks a little about some of the literature, in case you're interested, for the different aspects of airborne spread of a virus. And then we're going to have a section that is trying to characterize the airflow in speech. And our focus there is the transport that comes with what happens as you're speaking. And Manouk will do much of that, primarily focused on the experimental side. And then Simone will tell you what numerical simulations tell us. We also got very interested in small droplets that are formed that you hear people talking about. And so we'll show you experimentally some observations we've made in the lab that we believe are new for at least how some of the droplets are formed when you speak. And finally, we've tried to take this idea of social distancing and add time to it so we can talk about a space-time diagram for social distancing. And when you listen to this talk, what we'd like you to think about are fluid mechanical concepts. We believe we're helping add both new qualitative and quantitative insights, and our focus has largely been on the transport problem that might be carrying a virus or pathogen from one person to another. Okay, so as far as background about airborne spread, I know many of you have probably read a lot in the paper, so let's just tell you what our perspective has been. This is a very rich literature. It has a very long history. It's been talked about in many different contexts, whether you first read about cruise ships or spreading in offices. And there, the common term is asymptomatic spread when you're trying to talk about the spreading that happens when people don't have symptoms. Now, of course, coughing and sneezing is very important. It has a very beautiful literature as well. I'll comment about that later. But that typically is spreading when people have symptoms. And very early on in this disease, there was some hint that there was spreading when there were no symptoms present by anyone in the room. And I cite here on the slide an early case in Germany, which took place inside a conference room at a hotel where people got sick, although none of the hotel staff that was handling any of the glasses or plates or anything else, none of them got sick, but the people sitting at the table, some of them got sick. And as you probably are aware, there's been reports of large spreading in exercise classes. There was actually something in the paper just yesterday in the States of a large-scale spreading event associated with a fitness center. And these bring up the issue of spreading in air. And I will say that a very important question clearly is ventilation. And there's a very important literature that people are thinking about out there. I can comment on it later. We've been thinking more about the local problem, or what was sometimes going to call the direct interaction problem when you're with someone close to you. Now, there are a number of reports of so-called super spreading events where not just one or two people get sick, but many people get sick. An early one here, again in March, when we were first starting to think about this question of asymptomatic spread, took place in a choir. And you can read on the screen here a report from the paper that was published on it that roughly a large percentage of the people present in a small confined space were sickened. Unfortunately, a couple died, and the suggestion was that transmission was facilitated through the air. Okay, now we're not the first people to study this, of course. There's, as I mentioned, a rich literature in different aspects of what happens when you disturb the air around you, either by coughing, sneezing, or speaking. And so I list here two nice references. One already back in 2013, where people had already been doing some imaging, in this case, Schlieren imaging of sort of the cloud of exhaled air that you produce when you're speaking or sneezing. Lydia Berubia at MIT, who's just actually published a very nice review in Annual Reviews of Fluid Mechanics this year for 2021, has documented a lot of the work around the spread, the large scale spread that occurs when you're coughing and sneezing. So our focus, again, is going to be a little different, but what all of these problems have in common is that there's a transport problem that occurs as the air first leaves your mouth, as it propagates, perhaps as an isolated puff, or as it propagates as a continuous stream of fluid. And in all these cases, you'll see later that we talk about the propagation distance as T to a power. This kind of problem has a long history in fluid mechanics. And when air first leaves an orifice, or for example, a sound first leaves your mouth, people talk about the starting jet problem, where you expect a growth as the square root of time. On the other hand, when you have an isolated region propagating away from you, it's characterized as T to a power, where the power is a quarter. And that's often referred to as the puff regime. And we're going to try to point out how continuous speech is different than both of these, though it has common features. Now, if you go to the literature, a lot is known about speech, and there's certainly linguistic experts. And in fact, we took advantage of the fact that already back in the 60s, as Simone will show you later in the talk, people had characterized certain features of the airflow that we could use as initial conditions for our numerical simulations, where people had studied both the pressure and flow rate variations at the mouth during speech. And certain phonetic features, as Manouk already introduced this term plosives, certain phonetic features had been studied. Not a lot, but a few. And in particular, already 10 years ago, Sheldon Green's group had looked at the sound of P as in pa, and you'll hear more about that later. And that feature of phonetics, we're going to point out, we believe is important in these direct interactions because they have a significant influence on the propagation of the airflow when you speak. Further, if you go to the part of the literature that deals with buildings and indoor environments, there are research groups that have also tried to characterize very nicely both large-scale flows at the scale of room and small-scale flows at the scale of individuals. On the left, you see an image where people use mannequins as a way to try to understand something about small-scale interactions. And these groups have also looked at using Schlieren imaging to understand some of the individual features of small-scale flows. Here, sort of the starting jet that you see, which propagates, you can already get an indication as a vortex. So we're not working in a vacuum. We're working in an area where there have been a number of studies, both at small scale and large scales, and we're trying to add to that. We, in particular, want to tell you about what happens when a certain person who might be infected, that's the asymptomatic speaker on the left, which we call the host, might be breathing or exercising, and you're someone else in the room. Now, you can ask about what happens when ambient air currents are important. That's the large-scale ventilation problem. We're not going to think about that today. That's clearly an important problem. We're going to ask about the more localized problem of the social distance question, which is what happens when you're within 2 or 3 meters of someone? What are the kinds of transport characteristics that are important in that direct interaction problem? And there are two parts of this. There's the transport, and there are the droplets that everyone produces when you speak. And so I'm first going to just say that we've done a little work on droplets, but the droplet area has actually been well studied. And so I just want to tell you a little about that. And you might have already read some of this. The name Wells is perhaps the most important name in this field. He has worked back in the 1930s and many follow-up papers that is sort of the basis for what you hear about when people talk about the 6-foot rule. But already back in the 30s and 40s, you can find very beautiful papers, including high-speed imaging of what happens when you cough and sneeze. And in this magnificent paper from Jennison, he even has a couple images of what happens when you put a mask on. So there's a rich literature to draw on, and there's quantitative literature on this. For example, we cite here just one paper from Johnson and Maraska. Lydia Maraska also it continues to work very actively on this problem of the drops that are produced and the drop sizes and their distribution that are produced. And we're going to use that as an input for some of our work. But there's a connection to the droplet production in language, which is that different sounds produce different numbers of droplets, and how loud you speak has an effect on the number of droplets you produce. I've just cited here 2 papers from Bill Ristenpart's group that were published pre the current pandemic, but certainly relate very importantly to the pandemic because they start to connect droplet production and the droplet distributions to features of speech. So with that, I want to now say, okay, if there are droplets, how do they get from one person to another? And what are the features that we need to think about? And as you'll see later, what are some of the things you might be able to do to mitigate it? So I'm about to turn this over to Manouk Abkarian. I'll just say, if you want to read our work, it was published online a week ago and just yesterday in PNAS. But when you speak, the speeds you think about are the speeds coming out of your mouth. They're anywhere from a fraction of a meter per second to a few meters per second. A fluid mechanician thinks in terms of the Reynolds numbers, and the Reynolds numbers here are anywhere from a few hundred to several thousand. And our focus then is transport. How is this disease spreading at the scale of an individual? So with that, I'll turn it to you, Manouk.
Yeah. So indeed, the first type of experiments we tried to set initially was to observe the flow around the mouth of a speaker, and we used very classically a laser sheet, a pretty wide one, let's say over 2 meters and 1 meter in height. You can see in this image that the laser is on the top, is reflected to a mirror and passes inside the divergent lens that allows to spread it over a nice curtain of light. You can see in front a high-speed camera that will be at different angles to observe the different modalities that we used it to observe the flow. And if you can pass to the next, thank you, Howard. So we used basically the sheet in 2 different ways. On the left, we basically speak an interlocutor, and you can see is me on one side, speak parallel to the laser sheet. And to be able to observe the flow disturbances, we produce a fog around in the room, and this fog crosses the sheet, so you can have basically a slice of that fog. And this fog is produced just by a simple Halloween machine. And then when there is enough disturbance of that fluid flow, we can picture that, make a movie, and from the images we can correlate the deformation field of that fog and deduce like that the velocity profile induced by the speaking. And on the right, we use now a sheet that is perfectly, as you can see, black because there is no fog. And now a speaker is speaking basically orthogonal to that sheet, very close to it, let's say at 15 centimeters. And the goal here is to see more how aerosols leave the mouth of a speaker and the different conditions. And there's the last one that I didn't show here, where basically we will picture also with the big objective the mouth of a speaker. So if we just look very simply, as Howard just mentioned, the different characteristics of this problem. First, you have to think in terms of scale. So your mouth opening has an area of around 1 to 5 centimeters square. And a typical size around your mouth is 1 centimeter when you start to speak. And you can find in the literature, first of all, different data associated to the different airflow rate during normal, let's say, or calm breathing or during speaking. Also in the lab in Princeton, there is Philippe Bourrian that has a system that is developing for other aspects about ventilators, where you can measure this type of airflow. And you have to remember that basically you have between a fraction to 1 to 2 liters per second of exhalation peak flow rates. And these typical numbers will be the one that actually will be injected later on in the simulations of Simon. And again, the typical peak Reynolds number that you have for someone that is speaking will range between 700 to 3000. So the flow is basically mildly turbulent, let's say, at the maximum. Finally, since we are speaking about aerosols, when we speak about aerosols, now the definition has changed apparently in this literature. You can find many papers actually about that, but it's basically small droplets that can be between 1 micron up to 100 microns. And you can associate basically a stock number to this problem, which will basically compare the inertia of the droplet relatively to how it will be dragged by the flow around. And the stock number in these problems are small compared to one, the Stokes number, sorry. And so you have to think that all these small droplets follow the fluid that is leaving the mouth of a speaker, the airflow leaving the mouth of the speaker. So with this in mind, we started the first type of experiment, which is basically talking in and saying different type of sentences. And the most important one that we will try to show here, to not enter into detail, is that in some of the different sentences we voiced, when one word was pronounced with this plosive consonant, like P or B, you will see the emission of a strong vortex leaving the mouth. Here's an example, while saying, sing a song of sixpence. And so you don't see what happens to the sing a song because the laser sheet is not illuminating the mouth because of the angle. But later on, you see the pence leaving the mouth at a very high speed that can reach a meter or 1.5 meters per second, and induce a vortex and travel down as far as 1 meter. And if you try to measure the distance that vortex is traveling, you see two regimes of movement. At very, very short time scale, close to the mouth, let's say around 20 centimeters, you see that this distance goes as the square root of time for very short time scale. And this, as Howard mentioned, looks like what is called in this literature of jets a starting jet. But as soon as the P is pronounced, now you don't have any more momentum injected into the air in front of you. So this jet transforms into a puff. And can you come back, please, Howard? And this jet then propagates at with another power law that is much slower and reaches the meter you see in a second with this famous 1/4 power law. So as a message, basically this individual plosive induce strong vertical flows that can drive material up to a meter in front of the speaker. Then we were starting to look at sentences that are a little bit more complex. So if this plosive indeed induce this large-scale transport, what happens when you have a sentence that have many of these plosive? So we choose a typical sentence, which is Peter Piper picked a peck. And here you see a movie a little bit slowed down so that you can see each puffs leaving the mouth. So here is the Peter, and then you will see the second one, Piper. Oh, why it stops? Can you go back, please, Howard? Yeah, thank you. So Peter, and you see the first jet that is dragging the fog in front. So it's this slow down. And then you see the other puffs associated to the sentence that is short. The second one that reach faster the first vortex. So the Peter Piper, and another one again. And so what we were starting to see when we start to average these flows leaving the mouth for a head that is not moving and really a body that is static is a typical, as you can see on this image on the left, a typical conical like jet flow that will leave the mouth with an angle that will be around 20 degrees. And therefore the accumulation of these phonemes that are strong will create this jet-like flow that can reach easily 1 meter.
Okay, so now we try to understand what was all the accumulation of phonemes and the consequence. And to do that, we turn to numerical simulations that were performed. So it's a computation of the flow, and giving here in the first slide some indications of those simulations. So there are simulations of the Navier-Stokes equations. So predicting the flow in front of someone speaking in the incompressible regime, because compressibility does not matter at that levels of Mach number. And then because it's so turbulent simulations, we have turbulent modeling there. And we add many droplets actually as passive tracers to the flow to be ready able to observe the structure of the flow in 3D. And all that was done with a a solver that I've been developing in my group, which is called Yals2Bio, and which I use normally to blood flows, but which was adapted also to this configuration. So the type of simulations I'm going to show is the one sketched at the bottom. So you have a head model with a mouth exit that is fixed. This is an important assumption that we do, and we use an ellipse with a radii. It's 1 centimeter, 1.5 centimeters. So the cross section is a bit less than 5 centimeters square. And through this mouth exit is going to come out an unsteady flow, and we're going to predict the airflow, the flow speed, the turbulence, the droplet dispersion associated to the flow, given the assumptions. Then the big question is what to put as an inflow condition. And for that, we could rely on old papers measuring characteristics of the flow. So this paper measured many information about nasal flows, pressure, but also oral flow. And we use that oral flow for two particular sentences, like here, sing a song of sixpence. And what we did was to actually extract this oral flow and impose it in a simulation in a repeated way. So in the simulation, it's like having the signal of sing a song of sixpence, then a breathe in inhalation, then sing a song of sixpence again and breathe in, and this for cycles and cycles. And so this boundary condition was applied at the mouth of the head model, and we tested actually different kind of signals. So either breathing signals, so without all the fluctuations in the flow rate, and with two sentences you already heard about, so the sing a song of sixpence and the Peter Piper picked a peck, which were with different kinds of signals in terms of flow rate. And so here I'm going to show a movie with particles, with the tracers, and you will see actually the development of the flow in front of this head model. And so this is with the sing a song of sixpence sentence. And what happens is that it's very unsteady near the mouth. You see colors changing all the time. But what happens in the bulk of the jet is very different, very slow evolution. And you see here for about 9 to 10 cycles. And what happens is that you have very different characteristics, so very unsteady flow near the mouth, but far from the mouth, it's more like turbulent flow. Okay, it's varying over time, but you do not have the signature of the input flow that you put. Okay, and that's really important. The other important thing is that we recover also this conical structure that was also observed by averaging the experiment that Manouk showed a bit before. Then this actually made us think of those canonical flows in fluid mechanics, which we referred to as starting jets. So it's jets with constant momentum applied, and you see the unsteady development of the jet. This is here a sequence of different pictures for a same jet with constant image. And what you see is that the structure of the jet, the organization, is, well, quite similar to what we observed, actually. So this was also observed for different flow signals. So I told you there were two breathing-like signals at the top. So without many fluctuations in the speed, just exhaling and inhaling. And at the bottom, you have the two sentences. And the story is quite the same. You have cones, you have turbulent structure, and you forget what happens at the beginning near the mouth. And everything is integrated. You can see though differences between the different jets, and especially the angles seems wider, for example, for the Peter Piper picked a peck, and we seem to have an effect here of the fluctuation of velocity to have an important effect in widening the jet, opening it more, and having a larger angle. So with shorter and rougher jet in general during speech compared to breathing. So now we need to say a few words about what happens in starting jets, or more generally, what happens to inside a turbulent jet with constant inflow. Okay, so with constant inflow, you can have a turbulent jet with unsteady flow, but from the average point of view, it's steady. That's why it's written quasi-steady. And in those jets, you have a development with the conical development of the jet. So the radius is varying over distance like alpha, the angle of the jet, times distance. So the cross section, of course, is varying like alpha x square. And the speed of the jet is actually changing like 1 over x, okay, or like 1 over alpha x. And so this is what happens in a steady jet. This is what happens in the static jet with constant momentum influx. And now the question is, what is the velocity field that we have in our jets? So that's what we did. We extracted over the blue dashed line velocity profiles. So the problem, I have to say a few words before talking about the picture. The problem is that when you do turbulent simulation and unsteady flow, it's very difficult because nothing is ergodic here. It's difficult to make averages. So what we did in next slide was to time average over short times. So averages were built over cycles. So there were 4 seconds of cycles, and we time average over 4 seconds. We store this average as average for cycle 1, and then the same thing for cycle 2, etc., for all the cycles. And here I'm showing results for the average of cycle 4, the average of cycle 6, the average of cycle 8, etc., until 14. And those are the different colored plots that you see. And what you see is that actually the jet is growing, right? The orange one on the left is the one the soonest, for cycle 4, and the blue one is for cycle 6. So progressively the jet is going to grow, and the velocity, the speed over distance is going to increase over time and reach non-zero values further and further. And what you see is that little by little, you're building actually a curve which matches the curve of velocity as 1 over x, which is the model of the constant jet. And actually, it's true far enough from the mouth, but it's not true close to the mouth, where you have something specific, which is really related to what happens as unsteady, with the unsteady signal that you put. But far enough from the mouth, the model of a jet with constant inflow is valid and describes well our jets, our simulations. Now, once you have that, you can actually do a little bit of math to get the jet growth, the propagation over time. So this is L is the length of the jet along time. And here you have an equation that say that it varies as t, as the square root of t, right? And in the equation, you have an average velocity that comes up, the characteristic size, which is here like an equivalent radius of the mouth, and the jet angle, okay? And once you know that, you can start looking at the data. And basically here, I'm showing just the 2 lines. So it's a graph with time, with length over time, with proper non-dimensionalization. And puffs would vary like t to the power 1/4, and starting jets like t to the power 1/2. Now, if we add the simulations to that, what you see is this. So it's a lot of data there, but we can split in 2 groups. So the first group is the ones where what I simulated, what I computed was just saying once the sentence, like sing the song of sixpence, and that stopped the inflow. And those are the dashed dotted lines at the bottom, and they follow actually the curves of the puffs, like t to the 1/4. And once you have repeated sentences or repeated blowing, breathing from the mouth, what happens is that what you follow is actually the curve of the starting jets, of the constant momentum starting jets, even if it's not constant as an inflow. This is an excellent model to reproduce the trend that all the simulations have. And the great thing is that actually the experiments confirm that. So what Manouk did was to speak in front of the laser sheet, so perpendicular to the laser sheet, and measuring the time needed to perturb the flow at the laser sheet due to the sentences. And with different repetition of the sentences, different distance from the laser sheet, you could build like this, a curve of time, distance versus time, which is similar to the one shown on the left, except it's not in the log scale on the right. And you see that the scaling, so in the red curve, the scaling like distance with the square root of t also matches in the experiments. So the important thing is to understand that whatever you say, it's actually very important, very close to the mouth, but then the jet is going to integrate that and propagate as a mean jet, as a starting jet with constant input. And the important thing also is to talk about times. You could reach 1 meter after a second, but here you can reach 2 meters in 20 seconds. Okay, so the jet forms because of accumulation of speech, of phonemes. You will reach 20 or 30 seconds. In 20 seconds, you will reach the 2 meters distance.
At this point, we're going to turn to another study we did, which was continuing the idea of transport, but now trying to integrate back how droplets are formed as you speak. And Manouk, I believe you're going to do this section.
Yeah, so basically the question was to say, now we understand a little bit more transport. We just said, okay, there are phonetic features that are very important for this transport, either at 1 meter, as Simon said, or even further. But then are these features also important for the aerosol production, for this production of droplets? And so there is this literature that indeed exists, at least for this aerosol production. And we were surprised to see that there are only suggestions about the mechanisms of production of this droplet. The two that are salient are what is called the bursting of lung films. So apparently some models kind of worked numerically to how small air bubbles that will be due to mucus that will be clogging some of the arterioles deep in your lung will burst and produce small, let's say tiny micron-sized droplet, yes, that will be then pushed out by your exhalation. Or the second time which is what is called the flow over liquid films in airways, where basically the breathing will pull some liquid ligaments or filaments, I don't know, from surfaces, and maybe therefore break into droplet and again be exhaled when you breathe, for instance. But those were not clear since no direct observation was available. And on one side, there were also measurements done by some groups. So for example, Johnson, and Morovska, that we cited initially in the introduction, had this very nice setup where they have airflow passing the head of a speaker. And they report with what is called aerodynamic particle sizer, some particle number as a function of time emitted during speech or breathing. And more recently, the work of Bill Risenpart at UC Davis that showed that actually there is a relationship between the different modality of speaking. So if you say consonants or vowel and the number of droplets you will produce. And also, if you speak loud, apparently that number increased. And so we were really curious to see, okay, how many droplets are leaving the mouth of a speaker, not in a big wind tunnel where when you could have evaporation and this number could change, but really right at the exit of the mouth. And so we were inspired by a study that basically appeared at the same time we were working on that setup, that used a laser sheet again to observe at the exit of the mouth of a speaker the droplets. And we basically reproduce that experiment and measure this emission rate of droplets as a function of time. I don't know if you see the movie on the left. Here's an example. I don't know if we hear the sounds associated to the little flashes of light that you see when each of these aerosol droplets cross the sheet. So here, for example, different type of consonants will produce different number of droplets. And here I'm saying a vowel, and you see that no flashes appear. And here I go back to the P's, and there is droplet. So on the images on the right, here is an accumulation of different projection of different images of over 0.1 second to show how much this cloud is leaving your mouth when you say, for instance, pa, or when you say ta, which are basically two occlusive consonants. So what are these consonants? In speech, you can really separate the two types of sounds, what is called vowels, where you can maintain a sound just by the flapping of your vocal cords. like and you can maintain it a long time. And these consonants will basically, you have to interrupt the airflow either completely or with a little lick. And for example, the S is called a fricative, where a P, which has no lick, is called a plosive, because you have this very fast variation of pressure. And for this different type of consonants associated to just the vowel A, we measured the number of droplets produced as a function of time over 30 seconds. And what you can see in this graph, though there are variation in time because the amount of saliva that there is in the mouth is fluctuating when you speak more and more, like I'm doing here. For example, so Howard is drinking a glass of water also because he has a dry mouth, and it's the same for me. What you will see is that vowels that are these lower lines have the lower level of emission compared to consonants. And the number of droplets produced is much higher in orders of magnitude than what has been measured previously in these aerodynamic particle sizers. So then when we said, okay, and what's the specificity of this plosive consonant? So what is happening at the mouth of a speaker? So this is where we turned with a big zoom at the lips of someone saying, for example, papa. And here you see the first pa with a high-speed camera with a very big close-up, and here the scale bar that you see is 1 millimeter. And so in the first milliseconds, where the two lips that are pressed initially to increase the pressure in the oral cavity are being separated and reach a millimeter. So you can see on the images on the right, a film forms, and this film destabilizes into filaments that connect the two surfaces of the lips. But then when the air starts to leave the mouth, because the pa happens, then these filaments are being dragged by the fast airflow, deform, and can reach centimeter scale compared to the millimeter scale opening of the lips. And so we can see that on the curves of the length reported of this filament as a function of time. So once you have the filament form, you have a first regime of extension of this filament due to the opening of the lips up to, let's say, 4 millimeters. And then you have the airflow that appears that again multiplied by a factor 2 to 4 the length of these filaments that basically thin so much that they can reach the 80 micron to 50 micron diameter in size. And then these filaments will basically snap off the lips and be basically dragged away by the fast airflow and break into droplet while being transported. And here's again an image of this with very high illumination and very high speed to be able to capture the droplets. So the type of consonant also has a role on the stability of this filament. So instead of saying papa, now if you say baba, you will see that here you have a vibration, first of all, of the lips. And so the difference between these two bilabial consonants is that one uses the vibration of the vocal cord, which is the B. And you can try at home, if you say P and if you say B, you will feel your vocal cords vibrating. And this will basically produce very fast pressure variations, which will make the filaments wiggle, as you can see in the movie on in the upper right left corner of the image. And this will destabilize the filament earlier and produce bigger, for instance, droplets. And if you look at the other bilabial that is known, for instance, M, like mama, here the airflow does not pass from your mouth, but is actually liberated from your nose. And here filament extension happens, but the filaments break over the lips and are rarely dragged out from the mouth. So it's interesting that if your saliva, to think about that, if your saliva was only water, this phenomenon of filament extension will not happen. So if you take a drop of saliva in between your fingers, so this is the image on the left, you will see that your saliva has something specific, which is basically viscoelasticity. You can easily maintain a filament of saliva stable for almost a minute in between your fingers without airflow, obviously. While if you try to do that with a simple drop of water, you will have difficulties. And so the presence of very large biopolymers that are proteins called mucins for the mucin family, here the MUC5 and other type of proteins, will basically have a big role in this stabilizing phenomenon. So what happens when you drag like that a filament? Normally surface tension tries to minimize surface area, as you may know, and this will drive the breaking of the filament into very small droplets. But there are three processes that resist this instability. There is inertia, so the fluid, because of its density, doesn't want to move, so it should normally stay at least a filament for a while, and you can calculate the typical time scale associated to that first type of resistance. You have viscosity, because if you want to destabilize the filament, you will need flow to happen in these filaments and produce, for instance, beads and droplets over the filament. And so if you try to compare these two types of time scales, you can build a non-dimensional number in fluid mechanics called the Onnesor number. And in our case, without entering into detail, this number is very small compared to 1 for saliva. So it tells you that actually normally the only phenomenon that should take place is basically an inertia-dominated thinning of the filaments. But if you calculate this time scale, is of the order of a millisecond, which is much too fast compared to what we see in the movies I just showed you. So it tells you that indeed there is a third type of process that resists the thinning, which is these elastic stresses that develop due to the elongation of the filament. And this is a well-known phenomenon known in rheology, when you have very large polymers in the flow. And there's a typical time scale associated to this polymer, which is the relaxation time. And so now what you have to do is build another type of non-dimensional number, which is the ratio of this relaxation time versus the typical time scale of extension. And what we realize is that in this experiment, because saliva has relaxation time that can go from few to 10 of milliseconds, then we have this non-dimensional number, which is of the order of 1, which tells you that this is the phenomenon that is the most important resisting the thinning. And so once we saw that and we started to see the sequence of destabilization, we asked ourselves, is there a way to maybe, at least for this bilabial consonant, kill this phenomenon? So one way is to indeed change the rheology of saliva. And an easy way is to basically use a lip balm. When you put this lip balm over your lips, and if you had a little bit of saliva, this saliva will change composition. And so what we realized is that at least in the first utterances of saying pa, 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 when you have a lip balm, then the entire process of destabilization disappears. Or said differently, now the filaments cannot extend anymore on that scale and break very fast at the surface of the lip. So we were very happy to see that, though there is a little problem, is that this effect doesn't last for a long time. And so we need to work a lot on this, on the composition of the lip balm, if we wanted to use that as a very nice mitigation strategies, at least for bilabial consonants. At the end, what was interesting is, though we concentrated ourselves on the consonants, which is basically everything happening in this oral cavity where you have to block the airflow, we were asking ourselves, okay, for the vowels, we don't see very big droplets, and indeed some measure in the literature are showing droplets that could be at the micron size. And so how the glottis then, that is the only instrument that you are using to produce these droplets, could maybe generate such small droplets. And you can find in YouTube some movies, high-speed stroboscopic movies of glottis folds flapping. And what you realize is, if you look very carefully, you see that filaments seem to also develop in between the two folds when they are entering into contact. And there is a very nice mucus layer also in these folds. And so what we are realizing is that the instability we saw seems to happen also in the glottis. And at the end, since I brought in Princeton my saxophone, we started to look also at how maybe an instrument could produce droplets. And by just looking at the saxophone beak, where there is a reed, which is basically this very thin layer of wood that allows to produce the sound, with high-speed observation of the internal part of the reed, which is wet by saliva, and this is very important when you play saxophone, what you see is that in fractions of milliseconds, again, filament seems to develop and break down, and droplet are dragged orthogonal to the plane of the image. So this seems that this process seems to be general in all these cases. So now maybe, Howard, you can continue on the conclusion we draw from all these observations.
Thank you, Manouk. So at this point in the talk, I'm now going to try to put together the two things that you've heard about. You've heard about our thinking about transport at the scale of an individual and how we use experiments and numerical simulations to try to understand that not only qualitatively, but quantitatively. And also some work we've tried to do to add to the understanding of drop formation, in this case, linking it to rheology for what is coming out of your mouth and perhaps seeding the spread. And to do that, I'm going to try to take the social distancing features that you read about, the 6 feet or 1 meter or 2 meters, and ask, shouldn't you also be thinking about time? So I'm going to give you a space-time diagram that's informed by what I've just told you, what we've just learned. So you learn that when you breathe or speak, you tend to get conical features when you're speaking. And how might this impact asymptomatic spread? I don't think we have to look very far to realize that there are lots of events in our everyday life where you might be speaking in front of a person. The question is, should that worry you even though you can't see what's coming out of your mouth? And what are the risks that you face in these social situations? And so I'm now going to put together the quantitative pieces you've seen. And we did it following standard ideas in the literature for how people think about the risk when you have a virus in the air. You've seen that the speed from a speaker falls off as 1 over distance. Alpha is just the opening angle of the cone. You've seen that the area that's entrained goes up with the square of the distance. So what that will say to you is already at tens of centimeters away, your breath encompasses the size of a head of an individual in front of you. You're breathing or speaking with a certain flow rate. And we haven't said, but it follows from these ideas that anything you exhale, because you entrain air around you, has a concentration that falls off as 1 over distance. A consequence of that is you can then say, what does transport do if you're speaking in front of a person as you see the heads to the right, whether it's to the right in front of an experimental image or to the right in front of an simulation. I'll just say this simulation is color-coded so that there's a concentration unity at the mouth on your left and a concentration contour of 0.05 or 5% outlined. And you see that concentration contour is already at a scale that exceeds the head some distance away. I think this image is effectively 2 meters. Okay, so we want to then say it's not just distance, it's not just social distancing, separation distance, but time. And we estimate that by estimating the probability, as it's commonly done in this literature, as 1 minus the exponential of argument that asks you how close are you to the characteristic dose that people estimate for the number of virions you need to cause a disease. And we used the quantitative features of the conical cone to estimate the number of virions an asymptomatic person may be breathing out. It involves measurements that people have made for estimating how much virus there is in the saliva. It has an input that's how many droplets there are per unit volume of air. It has in it the flow rate that you have. And of course, it goes up linearly with time. And so you can then make a plot of the probability of being infected that involves the separation distance L and the time that you're interacting with someone. And you can make what we'll call a space-time diagram for social distancing. At any distance, shorter times are lower risk and longer times are higher risk. We've put a line here that is what happens when you have the number of virions equal to the critical number. And we based these quantitative features on an estimate, a conservative estimate for the critical number of virions being 100, which has been posited in a number of papers in the literature, which we cite in our work. And so we'd like to, certainly emphasize two things. You don't see what you speak, but your exhalation is affecting your environment. It affects it largely in some conical-like region in front of you, as long as you're not moving your head too much, and that the longer the time that you interact with someone, the higher the risk that you face, and you can quantify some aspects of that, at least using conservative models. And it is known that there's data that suggests that some people produce virus at concentrations 100 times larger than the average individual. What that would do in a diagram like this is reduce the time a factor of 100. If you took this diagram at 2 meters, although Manouk and Simone both showed you data that shows it's easy to get 3 meters after 20 seconds of speaking time. At 2 meters, if you interact with someone for 10 or 15 minutes, you're really at the limit that anyone, even with these conservative models, would say is high risk. If it were someone that had a lot of virus in their saliva, that 10 minutes would become some numbers of seconds, according to these sort of basic models. Okay, so with that, we hope you've liked this kind of threesome attempt to share with you the work we've been doing over the last months. We've told you about transport. We've told you about visualizing droplets formed at the mouth. We've tried to characterize a social distancing diagram. We have other ongoing work. The FLIR company, which has a camera that images CO2, we've been trying to use that to learn more about what happens when you wear masks. We realize there's already quite a bit of data out there on that. And we've been contacted by the Met Orchestra in New York City, who were furloughed in April. And if you'd like, we can show you what happens when you do this CO2 imaging with a camera from FLIR to look at an opera singer. With that, I think I can bring our talk to a close. We're very thankful to the NSF for funding, and we're happy to answer questions in any part of the discussion.
All right, Howard, thank you very much. You can unshare your screen so we can see a full panel of
yeah, if anyone's interested right now, I can show you the very quickly before we switch to other things. This is again imaging of the CO2 using a camera loaned to us by FLIR. This is an opera singer, Isabel Leonard, from the Met Orchestra in our lab.
Oh, Howard, we don't see you.
You have to share it.
Oh, I have to share
it, Howard.
I'm not, remember, Zhigang, I'm not technologically in the 21st century. Let me do it once more.
19th century scientist, no?
So I'll just say, we're at this point where we've taken data and we're trying to learn from these kind of studies as well. But I'll stop talking now, and we're happy to answer questions.
So Howard, remember, you're also discussion leader. You
Oh,
are
I'm
to
discussion
call
leader.
people.
Right.
So some people raise, so Dick already raised his blue hand, but you can assume everybody on the screen.
Okay,
wants
if
to
Dick
speak.
Arwin's present, I'd happily answer or try. Dick, if you have a question.
I have a couple of observations. For instance, the beautiful portrayal using CO2. The background CO2, a few hundred parts per million, and the exhaled CO2 on the order of 10%. So that's why you can see the breath. And the CO2 is a wonderful tracer. So
yeah, so I can say, Dick, we had realized this at some point. I think it was Manouk's idea. So we reached out to the FLIR company, and then with help from Elizabeth Bowman, who's a publicist for the Met Orchestra, and the great generosity of the FLIR company, they loaned us their camera to allow us to do some of this.
Yeah, I think that's great. And the other point I wanted to make, 2 points, is viral load measured by swab can be 1,000,000 times the median viral load for COVID-19 people. So interaction times can be very small if you happen to have the bad luck to meet one of these people with very high titers of SARS-CoV-2. And finally, in the writing of the infection probability as 1 minus e to the minus n over n naught, for all except highly certain infections, it's a lot more transparent to write that as just n over n naught. It's expanding the exponential. I put that into the chat. Thank you. This is great work. Thank you.
I guess I'm the discussion leader. We're certainly happy to answer questions. We've been doing all the talking for an hour. We're happy to answer some questions. I guess there's some questions in the chat. Piruz, do you want me to read your question, or would you like to ask it yourself?
I can do it either way. Can you hear me?
Sure,
Yeah.
please.
Okay, excellent talk. Very informative. A couple of quick questions I have. One is, for asymptomatic people, actually it's very well known the airborne particle forms in the lung, not in the mouth. It's really accumulation is what's going on. So I was wondering why you think it's important to have droplets form in a mouth that cause this, while the actual pathogen particles coming out of lung. So
I think you are, it's fallacious not to say that, because the question you are asking is basically assuming that what you said is totally true, and that's not totally true. It depends really on the studies you look at, and there are problems associated to this famous measurement of the number of droplets and size of the droplets of people breathing, and it's not yet clear if these droplets are really coming from any rupture process in the lung, or if there is, for instance, any condensation of the humid air leaving the mouth and then producing this 1 micron size droplet, which, if it was the case, they will have no viruses inside. So the question should be more, are we sure about all this small droplet emission just by breathing? And that's a very important question. And second, if it was only breathing, then no mask will really make a difference, because it will be all the leak that will infect us. And it will be interesting to check all this. I mean, it's not so obvious for me.
I have just a quick follow-up. Actually, this is for Simon. And since winter is coming, what's the effect of cold weather outside on all the simulation? I'm assuming everything was done isothermally. I'm going to mute.
Yeah, so thank you for the question. It's true that it was done isothermally. So we were not... It didn't look very important to do so, because in Manouk's experiments, it's true that we never saw a huge movement up, and so that's why we kept with this. Now it's true that temperature difference is gonna make things lift up, and in the future we'll have to account for that. Now, what we see is that those effects of temperature are all the more important, that you kill the initial momentum of your jets, especially for masks, for instance. If you've seen the last video with the mask, you see a huge movement up of the flow outside the mask, because actually you do not have the momentum that you give to the the jet. And yeah, so depending on what you're interested in, you have to account for that as a main effect or not.
Is that okay, Piruz? Okay, Teng Li, you have a question?
Yes, thank you for this wonderful talk, the TRIO talk, and it's very timely research. Thank you. I have a question about the last part Howard presented, where you are talking about the relation between the social distancing and as a function of time. I think that's very important. My question is along this line. So in this pandemic, people trying to social, so instead of inviting people to their house, and then they try to social outside. I do see in my neighborhood, people have this kind of walking bodies. So they walk together and while they're talking. So when you're walking and talking, then you have this somewhat a constant velocity, the two moving bodies while they are talking to each other. In that case, is there any correlation of the social distancing between these two walking bodies while they are talking and walking? I expect that when you are walking, probably because you are walking in a direction away from the
There's certainly one or two sort of macroscopic studies that people have done. We should have said that all our work in the lab was with the ventilation very low. We do comment that in our work that of course the outside flows will matter. That's sort of well known. Almost all the cases of transmission are indoors, not outdoors. And in your case, as you said, if you're walking side by side, then relative to you, the air is coming at you. It's tending to carry what you breathe out away. Now, of course, you probably turn towards the person to speak to them often. So there will be some risk, but it'll be much lower, one being outside and two by being somewhat separated as you walk. The issue in the model I pointed out, but Dick Garwin really emphasized it, is there are some people, a few people with a much larger viral load than average. And so we don't know who those people are, but the risk is not an easy one to assess because we're not all the same, but we can just produce these average models. And I should say the social distancing diagram that we've looked at, which is a sort of direct transport social distancing model. There are several groups around the world thinking about ventilation and how you make well-mixed room models to do this. The paper I know online is by Martin Bazant and John Bush from MIT. But you can ask similar questions where you're trying to say it's not just distance, but it's the time over which you might be in this environment that you should be trying to control.
So maybe we can walk faster. So
one thing I may add with walking is that actually the speed at which you walk is like a meter per second or something like that. So it's the same order of magnitude as the speed that everything comes out of your mouth. So already 1 meter per second is already, I think, very effective to carry the material, to transport things away from you and behind you.
That's very good. Okay, thank you.
Howard, there are questions. David Bell, Brian Cox. I know there are little blue hands you have to click, no?
I see. I'm failing. I see. Okay. I see.
Hello, is it me? I think. Thank you. Wonderful stuff. Really entertaining. The opera singer looks like very bad news.
In fact, we didn't mean it just to be entertaining. We actually wanted to hope people might find some value in it, but it's okay.
That too. Okay. Yes, value as well. Thank you. So the opera singer looks like really bad news. Here's the question, please. Is there a simple correlation, experimentally, ideally, but otherwise theoretically, between the flux of air out of somebody's mouth when they're talking or exercising or whatever, and the concentration of aerosol particles at a fixed distance from them? Does that account for would that account for the variation you see from person to person in their ability to spread infection? Or is that small compared to the variation you see because different people have different loads of virus inside them?
So just for your comment about the singer first, it's not such a bad news when you look at the flow rates leaving her mouth of this mezzo-soprano, because most of what she does is to control the airflow so much and so well that she uses all that airflow just to produce the sound, but the air is not going so far. And since she's actually vocalizing a lot and making a lot of these vibratos, as we say in English, actually the flow is not as big as if she was actually pronouncing very well the consonants and using all her airflow to make, I don't know, to say Peter Piper picked a peck, though maybe it will depend on the opera. To come back to your question about the number of droplets, yeah, indeed, the number increases when, for instance, it seems the speaker speaks louder. So that for example, we cited the work of Bill Ristenpart, where he tried to do that with these aerodynamic particle sizers. there is also this paper from Arfinrud group where they show that saying very strongly, stay healthy, produces a huge amount of droplet crossing the sheet. So there is a relationship. The question now is, when you speak loud, do you produce bigger droplet also, or just more droplet that can be also small enough to be transported far away? And that's a question still to be.
Can I just quickly add, and then we'll go to another question, Brian, that the quantitative relationship we give is backed up both by experiments and simulations. The basic idea as you speak, independent of how you speak, is you will get this conical region in front of you. As soon as you have that, the concentration of exhaled material, whatever is coming out of your mouth, is going to fall off as 1 over distance. That 1 over distance accounts for the air, the ambient air that you're entraining. What's coming out of your mouth, independent of what the mechanism is that gets it out of your mouth, is going to involve aerosol or droplets, which have some virus in them, and a number of droplets. And I think the largest uncertainty is not the fluid mechanical transport part, it's the input, it's the virus that's in the droplets and a bit with loudness that's coming out of your mouth.
Yeah, right. Thank you very much.
Okay, I see David Bell, you have your hand up. Hello, David.
Hi, Howard, how are you doing? I'm just wondering if you've done any thoughts about speaking through a mask. What would be the effect of the mask on actually
so
speaking?
we have a lot of imaging on that, but you can find online both some research papers and also just YouTube videos. The mask effectively cuts off the jet. The mask essentially makes it so that the only thing leaving the mask is a low flow rate out uniformly, more or less in front of you, and leakage, and you look more like a local plume than anything else. So the mask has a big effect on the flow, and it also has twofold effect on the droplets. Fewer droplets get out, and because you're wearing a mask, fewer droplets get in. Quite often stated as just a quadratic effect to protect you if everyone is wearing a mask. So
are you saying it cuts down by like an order of magnitude, or what's the
the statement is if masks reduce to 1 over 10 the amount of droplets coming out, that's an estimate. Then if everyone is wearing a mask, then everyone's protected 1 over 10 squared, so 100 times more.
Just a note, if you scream and you try to not move your head, you can reach easily even more than a meter, especially if you use explosive. But if you scream with a mask, as long as you don't have leak, the airflow doesn't go further than 15 centimeters away. And then what basically controls the dynamics of this spreading of whatever could pass, imagine, through the mask is now only temperature dominated, which goes back to the initial question of what's the role of temperature. Here it will be very important because the impulse of the jet is so low that now it's only temperature that is driving the movement of that air.
Yeah, there was a report in the news this morning from Riken, the Japanese university, about the effect of humidity on spreading, saying that lower humidity allows for greater spread, which I found interesting.
Yeah.
I didn't see the paper.
There's a big literature on humidity over years. My impression is it's not as straightforward as one might think. I know Lindsay Marr, who's a well-known expert in aerosols, has published on this. There's work in the fluid mechanics literature recently from Detlef Lofs's group trying to ask about many droplets in and how that affects single droplet estimates. Roland Netz's group has several papers on recent. So there's a big literature on humidity. I don't think it's as straightforward as one might think, but it's certainly an important parameter.
Really nice stuff, guys. Really nice stuff.
Ahmed, then Tahir, and then Eberhard.
Okay. Hello, everyone. I would like first to thank you for this fascinating talk. I am at the University of Illinois, and I have been working on modeling COVID-19 in university environment. And the critical component of our model is airborne transmission, because on one hand, people talk about R node, but R node cannot explain over dispersion and cannot explain super spreader. So it's just this airborne transmission mechanism is actually the nexus that generates this. I have one comment and one question. The comment is related to what Professor Dick Garwin and you have pointed out about the variability between different individuals. And I would say that it also varies within the same individual as a function of the stage of infectiousness. So if you meet somebody early on after catching the virus, probably you will need a long exposure time to get infected. But as the virus builds in inside and reaches the peak and so on, this duration becomes smaller. So super spreader events happen because you met the wrong person at the wrong time specifically. But the question is probably related to droplets versus aerosol. And I wonder if you have been looking at the aerosol transmission on the smaller side of the spectrum, 5 microns and less, and how is the size distribution of the droplets in that
So
limit?
I just going to answer quickly to give someone else a chance. That subject, I think, has been pretty well studied. From our perspective, we just assumed, for the reasons that Manouk and Simone explained, that the droplets are small enough that they, on the scale of the direct interaction, they're passive tracers. And so we didn't worry about what the detailed distributions are. When the droplets come out of your mouth, the smaller ones typically will evaporate and get even smaller. So we just said there are droplets, they're going to be small ones, they're going to get transported to a first approximation at the scale of a few meters, they're passive tracers. And that was how we decided to deal with that part of the problem.
So then one quick follow-up, then this 2 meters or 6 feet distance, how do you view it then?
Well, we showed you a graph. Why should you take it seriously? Manouk and Simone show you that if you go to our lab in a low ventilated environment and speak for 30 seconds, some of the vortices have carried out 3 meters.
Yes, exactly. So in fact,
so for us, it's not a wall. It's just we don't see what we speak, so we don't have that. And as you know, it's known sort of where 2 meters got introduced into the world. It's just, it's not obvious for this problem, which may have a significant amount of asymptomatic transmission, that is viewed as the standard spacing no matter what you do.
Okay, thank you.
Someone else, Tahir, you had your hand up?
Yeah, in fact, Ahmad just asked half of my questions, or more than half of the questions. Regarding the humidity, I know it's a big literature, but I would expect that as a function of temperature and humidity, there would be some Marangoni flow within the droplets, right? At the surface or near the surface. Would that influence the transport, or because
I think that's so far down at the scale of the questions you could ask, it would have an effect at the scale maybe of a droplet. I can't imagine it's an order 1 question to ask.
But you will need a gradient of temperature. You will need a very big local gradient of temperature to have any effect, no? At the scale of the droplet, huh?
Right.
Microns or, so it's a big gradient, imagine.
Yeah, the reason I'm asking this is I come from Bangladesh, and we were initially thinking that there'll be lots of people infected and dead, so high population density. And it turned out to be the other way. And very few deaths and very few infection rate also, although the infection is everywhere in the whole country. And it remains as a question that something which has, of course, the temperature is much higher, humidity is very high. Is that something helping the population? They have invested.
I mean, it could be. I know there's literature on this. There's also literature about the age distribution of the virus in these countries. So, you know, I'm not the right person to try to attempt an explanation for that. But I know there's discussion, although I think it's more focused on the age distribution of the population than the background temperature in the environment.
Okay. All right. Thank you.
Okay. Eberhard.
Hi. Thanks. Nice talk. Nice stuff. So my question is the following. So in the opera movie, it was very clear that the room air was, not even getting the CO2 get very far into the room and being distributed into the room. So have you actually already worked on what the room air does to the mixing of the aerosols?
I mean, the short answer is no, but we are trying to head towards that with our colleagues at the Met Orchestra who reached out because like other orchestras, at least in the US, they don't have the support of their government. So they're looking for strategies to try to be able to both practice and perform. So obviously one has to get there, but not there yet. And others also, other very good groups are thinking about these important questions.
Including me. but that's okay.
Yeah, wonderful, Eberhard. The more the merrier. Okay, Manouk and Simone, I'm going to sign off. I have to go teach my class. So I'm going to leave, but I'm thankful that we had this opportunity. Manouk and Simone, you guys now are in charge.
Okay.
And Zhigang, thank you again for making this possible.
So who is next? Because we had many of the raised hand. I think there is Jimmy and then Tian, I think, or Yaling. There are many actually. I don't know which one.
All right. Let me ask the question first. Actually, this is related to Manouk, to what you showed. You showed that when you put lip balm, you would prevent droplets from forming. And there's actually evidence, or there's observation that men are more susceptible to COVID-19 than women. Is it because of the lipsticks, or? But if
it's
so,
a very good question.
Okay, if so, do we have evidence that for flu, which is also passed on, transmitted by droplets, is it also true that men are more easily infected in the flu season than women?
That I don't know. That I don't know. I will say that for the lipstick,
that's discrimination, right?
It is not so obvious, because the difference between the lipstick and again depend on the composition of the lipstick and these lip balms is that, for instance, many lipsticks are actually very tightly adhered to the lips, and so they absorb less water. But there are lipsticks that do the inverse. They absorb water and they will become more mushy. And it makes like this glossy. I'm talking about that like I'm an expert, but it's not the case. But I saw some lipsticks, and so it's a good question. Are lipsticks, for instance, a good way to play on that? I don't know, and I would like to explore that in the next months, I hope. And maybe there is again a composition or something that could help maintain this effect that disappears after 30 seconds or 1 minute, that you say pa 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 pa, you see the number of droplets will increase while it was decreased initially. And so maybe a lipstick composition could be much better than a lip balm composition. I cannot answer for the moment to that question, but it's a very good question.
Okay, thank you. Very interesting talk.
Thank you. So then I don't know.
I have a class to teach, so bye-bye.
Oh, bye. So Tian, who is Tian, Dialing, Ahmed, no, already talked, or Brian also, they already talked, or it's a new question, I don't know. So let's see, Tian.
So maybe, yeah, Tian is here. Thank you for this wonderful talk. Very, very interesting. This is Tian. I'm from Canada. I'm at the University of Alberta. Really interesting talk. And my question might be naive. I'm not really in the fluid dynamic area, but I'm curious about the interactions between the jets. So what you were talking about is mainly the jets from one person. But if two person or multiple person are having a conversation, I'm wondering how that interaction of the jets would come into play. I'm just naively thinking, if I'm having a conversation with someone, would it help for me to wait a few seconds for that person to finish before I start talking? Or I wonder if you could comment on that. Thank you.
It's a very good question, and I will let Simon talk about that, because he's thinking a lot about this problem actually. So it's not a naive question; it's a very good question.
Yeah, it's actually a very good question, and we've started thinking about that actually. So you can think of several sub problems. The first thing is that imagine that a person speaks in front of you, and you just breathe. Then you normally will breathe with the nose mainly, and this, for example, would start. That would be the first step to look at interactions. What is the effect of having these jets coming out of your nose on the environment? We think because of the direction of the jet is not going to change everything to the story. And what is more than the step in which you will add really complexity is in a true conversation. If you exchange, you know, if you change the speaking person, then what we think is that you should be the one speaking, you know, all the time to protect yourself. So if you're not a very talkative person, this needs to change, you know, need to speak, and certainly not waiting to the other one to finish and wait, because probably you're gonna, you know, entrain air around you and push the thing. That's the global naive way of thinking. Now we really have to turn that into science, you know, and try to measure the effect of the speech in your environment. Is it going to change everything? Is it going to blow everything away? The same thing with the breathing, and this is something we started, but just started.
So Simone, that's exactly what Donald Trump did in his debate. Keep talking, interrupting.
Yeah, well, apparently it's not protective enough, or.
Thank you, thank you.
Thank you.
Then Yaling, I think, has also a hand raised.
Yeah. This is Yang Lu from Lehigh University. So I'm mostly working in the microscale fluid dynamics. So I have a question about this microscale behavior, also about interaction, what Tian mentioned, but in a small scale. So those droplets, you know, they're going to evaporate. They're also going to collision with each other, or maybe merge with each other, right? Or even when they spread out, I don't know, when you come for infection, are you talking about like contact with the face, or you talk about inhale into another person's nose? So can you explain a little bit about the microscale dynamics involved?
So for what you are saying about the interaction between droplets is not so easy, because you have to remember talking is not sneezing. It's micro sneezing, if you want. So in a sense, you micro sneeze. So therefore you don't produce billions of droplets, as you could see in these nice movies of sneezing or even coughing strongly. So first of all, the probability of this droplet to fuse or merge will be very low. And second, because of the typical flow and their scale relatively to the turbulent flow, maybe Simon can add about that, the chances are very low for them to coalesce.
Yeah, they do not have relative velocity, actually, because at their scale they're going to be carried by the flow, mainly at the micron scale. So all what you describe is more relevant to sneezing, for example, where you will have like millimeter scale droplets, and they can interact, they can merge, and etc. So we at least think of the small droplets and aerosols as really small isolated particles which won't interact with each other. And for then the deposition or inhalation and all that, this is a good question.
I think more a biology question in a sense, because what the portal for entrance for the virus, is this receptor that is called ACE2. And this receptor is basically present in many of the cells in your nasal cavity and in your mouth, but it's not in your dead. For the moment, is not proven that is on your dead cells of your skin, for instance. So, but if it enters, for example, your eyes and go deep in it, maybe those cells have it too. But the highest number of these ACE2 proteins are present more in the oral cavity and then in the lungs. And actually, when the virus reaches the lung, that can be very troublesome for you.
Thank you.
So another Piruz is asking another question, I think. Yeah.
So I was wondering, because most of these aerosols or droplets are from 100 nanometer to, let's say, a micron or two, and that's really take your Nusselt number around 0.1 and even higher, which means slip velocity or even more on a more dilute situation. I was wondering if simulation considered that boundary condition, even though the Marangoni flow and things like this, I don't think it's going to happen because they're mostly very viscous droplets as well. But certainly they are in a slip boundary condition. But I'm not sure if the simulation take care of it on its own, or because that could be effective on a transport of the particles.
Yeah, so it's It's a good question. At the moment, the particles I put are just tracers. So we even ignore actually gravity because we're thinking of direct transport. So at the scale of a few tens of seconds. So they're just tracers transported by the flow. Now, obviously, to go towards more physics in the droplets behavior and also longer times, we will need to add gravity, evaporation, and maybe other effects as you described at a smaller scale. But then I'm not sure we can also do macroscopic simulations like that at the scales of meters if you go towards the small details at the levels of the drop. So maybe this has to be modeled or accounted for by a model coming from microscopic simulations done apart.
And just a comment also about what you just said again, this 0.1 micron that you're talking about, or even 1 micron size droplet in an environment that is not too humid. So again, it goes back to the other question about humidity. These type of droplets are known to evaporate super fast. And when I say super fast, it's under the second. And so the question is, they leave behind what in this literature is called a fomite. And the big question, it is almost a biological question, is are these infectious? And so therefore, is it even important to talk about these objects? Relatively to the bigger ones, that first of all, if they are not too big, will not sediment. Second of all, they will continuously dry, but not be too heavy to fall. And those will leave the state of this lipid membrane that is actually making the structure of the virus in a better state to be infectious than when you have this crumple of mucin and completely crossed structure that is the fomite. Doesn't mean that fomites are not infectious, but this is the question we should ask ourselves. And here I think biologists could be also the good people to ask to.
Yeah, it seems like if you think about the airborne particle, people consider it submicron or a couple of microns smaller. And we are leaning more toward the airborne particles versus droplets. But also, I agree with you, they're also, nobody knows. There is such a gray area between these particles, and they both exist and they coexist. The question is, when we talk about the airborne particles, do we have to look at sub 1 micron, or still the larger ones can work? So
I will say no for very simple soft matter reasons, in a sense that you have salts and you have also many proteins in your saliva, and you have this virus that first of all is not so small, and it's between 50 nanometer to 100 nanometer in size. And so if you're telling me you're at 0.1 micron, you are the size of the virus itself. So if it's surrounded by proteins while it's drying, the osmotic stresses of that object are huge. So the question is how this thing that is floppy will resist to all that. So
it's somehow come back with the original question that you're making assumption everything comes out of saliva, but we really don't know, right? It can come out of lung, and it could be viruses with some kind of mucus thing between them that comes. It's not like really nice bright shape of a droplet with viruses inside of it. So I think we don't know. I think, at least in my opinion, a lot of things we still don't know.
I think that if you look at biologists, they do tests on saliva, they do tests on mucus, they do tests on the saliva of the mouth, because it is present in a huge quantity. We're speaking about titers just before, is really because it's present there already, and especially for asymptomatic people.
Yeah, but I think there is recent reports saying that those airborne can suspend for hours. It's not like really what we believed before, for minutes, or I think the maximum time you talk about there in 30 minutes or so, right? But there's small airborne, not even particles, but more like tiny particles that suspended for hours. And they might still be infectious because they might be those large droplets that evaporate, but the virus might still condense over there.
So that's the question. That's a very important, and I think it's at the limit again.
All right, Simon, you have to take over.
Yeah. The droplets evaporate in a time of milliseconds. And they come from physiological fluids. even in the lung. So they have 1% saline, and then they have polysaccharides as well. And so if a droplet evaporates to dryness, it's 1/5 its initial size. If it evaporates to a point where vapor pressure is just low and equal to the ambient humidity, partial pressure of water, it may be only a factor 3 smaller than initially. But there's still a very small concentration of the virus, of virions. It's mostly other material. And the fomites, if these things are too small to fall, they remain virulent for several hours by experiment in the atmosphere. They're transported through the ventilation system. And the last point I want to make now is that you have buoyancy from the exhaled breath and the environment of people. Each person is 100 watts. And so that's put into the air, not mostly by radiation, but by contact and by exhaled breath. So there is vertical acceleration and then initial velocity, almost a meter per second in the exhaled breath. That should be visible in the CO2, for instance.
So we don't have other questions, I see, no? No, I think I don't see any blue hands.
Yeah.
Ziga,
yes.
Yeah, I have a question.
Right. Our simple question was you didn't talk too many details about your simulation itself. Your simulation is just simulating the flow of air. Is that right?
Yes. So it's just air. So here it's a bit disturbing because I only show particles, but actually the main effort is solving the flow of air, the turbulent flow of air. And the particles was an effective way, in a sense, to show the growth of the jet in a more like a 3D way. But the effort is like continuum mechanics applied to so classical CFD to compute the flow of air and then add the particles as passive tracers.
Yeah, thank you. I have two follow-up questions. So that's great. I like your justification, whatever inside these particles probably just flow with the air. I guess you guys probably estimate the size such that airflow probably captures the main flow, whatever the nature of particle is. But the question is, now from your simulation, all these preventative measures, such as mask, we already talked a little bit about, also these plastic separator.
Yeah.
Are they effective?
So compared to masks, yes. I mean they definitely break the momentum forward, and then you add the filtering effect for the droplets. So it's really the most effective thing. Then for the protection, it's going to be different. So the protection will get your biggest droplets. So yeah, the sputter, things that you see at the naked eye. Then because for the first, the smallest droplets, aerosols are mostly going to follow the airflow. So they're going to be deflected, but they're going to flow out. So you do not have filtering effect in that sense. And then the other thing is that you do not completely kill the momentum for what you redirected. So this will, I think, disperse more also the droplets, although you do not have this forward momentum. Now, recently I have seen protection just from the bottom, which I think are not really serious. Mm-hmm. I would say like protection like that should be very effective if you have to be very close to a person, for example. Mm-hmm. So maybe for people in medical care who have to take care of other people, being very, very close. Now that may be effective. Also, people talk about the protective effect for the eyes, because you do not get the projections also in the eyes, and mask doesn't protect the eye. Yeah, but so short answer is masks are much better, especially because of filtering, with the regarding the protection that they give.
Now, how about this big plastic sheet? So you see transparent sheet, you see in shopping center, this kind of place. These sheet, are they effective?
Well, I would say it depends exactly on the situation. It's very difficult to talk about protection in absolute manner, you know. But if you separate the air regions, this is certainly going to help. You limit the exchanges, the convection to a region. Okay, so you separate regions. Now, if it's a large sheet but not completely occlusive, you're going to separate for some time, and then the airflow, the ambient airflow, are going to say if it's protective, if it's really protective or not.
Thank you. Yeah. Okay.
So do we see other questions? Here, no. No, I don't see other questions, so I'm missing them.
There is Isabel. Isabel, are you there?
I am. Do you hear me?
Yes.
Yeah.
Okay, I'm trying to start my video. Sorry. So I am a student in linguistics. I'm just a beginner at Princeton University, but I was wondering if you have considered involving linguists and experts in the field, not only just to correlate the sounds with the diffusion of COVID-19, but also the type of languages to COVID-19.
Definitely. So when we started all this discussion with Howard, so as I told you, my wife studied linguistics, actually applied linguistics.
Okay.
She was the first one to suggest actually the importance of plosive sounds maybe in this problem, and we were with Howard like really stunned. Yeah, maybe that's the key for at least large scale transport. And but then when you start to say that, you start to think to other questions like, oh yeah, okay, see, if plosive are important, are the frequency of using plosive like P and B's important in a given text, and therefore are languages more prone to pronounce those, and are they more efficient to transport on long length scale aerosols? Good question. I have no idea. So that's why it will be very interesting to indeed talk with many linguists. So I'm in contact in Paris to this CNRS team that is working in phonetics. But the question is really wider. Is really about linguistics and this transmission of COVID, since humans need to talk. And we understood that actually without consonants, it's impossible to basically exchange information.
Thank you.
I have another practical question. It's so I assume the things you're studying, of course, is motivated by COVID, but it is correct. The conclusion should be applicable to all kinds of viruses, right? Flu season, this kind
and not only all kind of viruses, but we speak about humans, isn't it? But animals are in the play, no?
Yeah,
So we speak about animals transmit to other animals, and then the one that we consume are transmitting to the humans. Yeah. And so the question is actually, if a bat screams, what is the load of virus it emits? Does it produce aerosols? What's the speed? Are they small? Are they big? Do they dry? Are they composed of saliva? The same. I mean, you start to multiply the number of questions, because now you are not just focalizing on humans, but also on cows, for instance, that also transmit diseases. So
another thing, it's outside your talk directly, but you guys must have read literature thoroughly. So yeah, for all this excitement was attention to protection. The best we can offer is mask, right? Somebody must have thought about innovation in what else can you do? Now you understand these particles better. Do people talk about anything other than mask? That mask is the thing now. Anything else?
I guess it's also because we don't really know at the end of the day, again, the transmission potential of all these, because we need to bring back the biology in it.
Yeah.
And what we just did is to bring back fluid mechanics in the problem. Yeah. So now the two need to talk, because the transport of all these pathogens, the question is, what is the structure, the survival inside this? So now, not only fluid mechanics should play a role, but soft matter, biology. And you start to see that all these fields need to talk for this problem to be better understood, and therefore to develop new strategies. So you see, just thinking about the wetting or the rheology over the lips gives you an idea. Not very good. Maybe we should think about chewing gums. I don't know. You see what I mean? To go further in the question, but it's only by then digging in these problems and asking with new, in a new light, these questions, that we will get maybe answers to the question you are asking. For what Simon can say is that people are indeed thinking about, I guess, how to capture, for example, aerosols with other aerosols. It's another question.
Yeah, and also I think that now there is really an increased interest in how to ventilate. I mean, you add a parameter to the way people ventilate buildings. They have ways of doing that. They have methods. They have rules which do not account for spreading of a virus in a building. And now, if you add this, maybe the rules for ventilating, the way you ventilate the I don't know, maybe the ventilation system itself should be revised. You have also questions of filters, how you filter the air in a room, and you can also think in terms of fluid mechanics of where to put filters, for instance, things like that. Can we define rules? Can we optimize the way they're placed? So you can act at the level of the people and also at the level of the buildings, of the rules, of the rooms.
Yeah, of course. I'm asking this. I'm just thinking COVID, of course, is the biggest thing at the moment. But just think about a common flu every year is a loss of time, energy. If one can do something more effective than masks, because people are, at least Americans, are not going to wear masks for flu, right? If you can invent something more effective, then that would be huge. We also have a newcomer, Li Chen. You want to say something? You're muted, Li Chen.
Hi, hi, professors. Yeah, sorry, I didn't catch the whole talk. I catch the left part of talk because I attended another talk before. So, but I'm interested in your talks. They are very nice. So I'm in France, in Paris now. So, you know, in Paris, I found that, you know, they wearing the mask, but this mask is not the, you know, the medical mask. It is fabric mask. So this is a mask from my institute, then it is delivered to us. So then I you know, when I talked to them, I said, this mask is not effective. They said, no, they tested that. This mask is so effective. It's even better than the medical mask, you know. So for me, I just, when, you know, the question is here, I'm wondering, is it effective enough, or it's better, or it's worse? And how thick or what kind of material could make this kind of mask as effective as that one or better than that one? You know, I also have another mask made of silk. I bought it from China. So I don't think that mask can, you know, provide the droplet from my mouth, you know. Yeah, thank you.
So I don't know, but there has been some literature about that, at least for the filtration process, indeed, of this type of tissues. And clearly the masks, for example, that are very, like the bandanas that sometimes people put, or like the silk that you are talking about, are really bad filters. And so what happens is that, first of all, the number of particles passing are, I don't know, many folds bigger than when you use these surgical masks. Then the one that are tissues with several layers reduce, and they are, let's say, they leave, they filtrate 95% of whatever passes, but not 99% compared to the surgical mask. And there are these FFP2 masks that filter really a lot. The problem is that you cannot spend 8 hours with that thing on your mouth at work. You will get crazy. And so the question is, I guess you actually raised a good point here. Sociologists also should intervene in the problem. Is that people, as Jigang said, don't want to wear that type of mask, or they will like it to be nice and beautiful, or some people don't support the fact that they don't see the mouth of the person talking, so they will prefer to put this just the screen, because like this you can see them talk. And so we are in presence of people that build beliefs, and so they believe that it helps. So putting a bandana, but then you could say, what's the best, a bandana or no mask at all? But then for that choice, I will at least bet on the bandana. The problem is, if you put something, you feel safe, and you should not, because the bandana is not a perfect protection, for instance. And so again, it's a sociological problem, almost psychological.
Yeah, but to complete a little bit, I think compared to if you think in terms of our talk, for instance, any mask is going to help killing the momentum of your jet in front of you when you speak. So for example, I use kind of fabric masks in the street. You know, if I meet someone, then I think I won't have this jets, you know, going out of my mouth and going with strength towards the person I'm talking to. And then I will have probably leaks everywhere, but things that will be carried with the wind. And it's probably more an opinion thing. But when I'm more with people for a longer time in a room, if I'm far away, I use surgical mask, because well, if fabric masks were more effective, doctors would wear them. Okay, not the surgical mask. So with the surgical mask, you have better filtering. So you have the two effects of you know, stopping the direct transport and also having better filtering. Then also, I think you have the big question of leaks. Sometimes you have masks which are said to filter very well, but they're tested maybe by looking at what they filter when the whole flow goes through. But if they, for example, the pressure, if the pressure losses, you know, associated with multiple layers are too high, actually the flow doesn't go through. It leaks everywhere, and you do not filter anything, because actually nothing passes through the mask.
Sounds like the world is ready for transparent mask. Only block, seriously, only block droplets, do not block air, and do not block light. I guess it doesn't against physics, right? It's possible. It's just we need to put mind to it.
No, you see, it's a material question now.
Yeah, it is.
Yep.
It is.
How do you make a porous material that is transparent?
A lot of materials are transparent. It just
exactly.
Refraction.
So you have to choose correctly.
Yeah, refraction constant bomb for the air. Yeah. Well, we can work on it. Yeah. Okay. All right. So do we have any other questions? Yes. Oh, yes.
So if I may ask, it's not about science, it's about communication of science. Because what I find very, very interesting in your talk is you use some experiments that are, I think, interesting to the, also interesting to the community, right? For example, the lip balm. That's amazing. And also you use, right, Peter Piper picked the pack. I think it's not only interesting to adults, but also children. Because we know there's still people, you know, fundamentally against these measures. I wonder if you thought of like community experiments, you know, the fluids is works of trans.
Yeah, Tian, we couldn't follow you. Yeah. So
again,
now you're better. Repeat.
Now I'm better. Oh, okay.
Turn off the camera or something.
Maybe my internet.
Okay, that's better.
So I was asking whether you thought of communicating your interesting interesting. Do I still have problem connecting?
No,
that's okay.
I will hear you.
Sorry, sorry about that. I was asking whether you thought of communicating your interesting experiments to the broader community, because you really used very interesting tongue twisters. Results with the lip balm. I think it's really interesting to the broader community, and I think the broader community need that. A lot of people are still not accepting things like mask, right? The protective measures. So I think it would be very nice to communicate those results to the broader community. I just wonder if you are thinking of that.
We're not thinking, we are submerged about that. People actually contacted us. Many journalists that have blog in science wanted to understand. More less scientific journalists that had more problems to understand, but still, because it's at the end, the message is pretty simple, they get it. And they told us actually, oh, we love that study about COVID because it's one of the few we understand. So it was interesting to hear that from a journalist. And indeed it helps, and journalists are in need of actually advice for them to give also to the greater public. And it's not easy because we are not safety experts. We just studied one problem in a given condition of the lab, already teaches us something about transport, opens many questions that we hope that all the community will engage in. We can advance as a group, not just alone. But then you are in this limit where you have to give opinions mixed up with what you discovered, and it's tricky. It's tricky. You just all did that to us. We just asked us, what do we do with a mask that is not filtering? And we didn't study mask. What we published is about, we have a paper about masks. It's not yet out, and other groups have published on masks. So communication could be tricky, but we did our job. We tried as much as we could to talk about that. And they are still, I will talk with an Australian journalist on Friday, and I guess Simon also has some that try to write papers about it because of what you said.
Yeah, actually, I have a specific question about this lip balm. Without balm, you have these, I guess, a liquid form a column.
Yep.
Of course, occasionally I see columns, but is that a generic, often happen, or it's just a rare?
For this is all the time. If you so another part that we didn't show in the presentation and that is in the paper, the other type of consonant like this dentalveolar, which is basically using your tongue and the ridge between your palate and your teeth. When you say d or t, you don't use your lips. So here, a lip balm will not be useful for you. And so what happens in that case, you have the mechanism is a little bit different. So there is first the filaments, again, the film that breaks into filaments, and the filament being dragged away by the airflow. But since the saliva is in much more quantities than in on the lips, what happens is often you have also little bubbles that grow. And so the bubble bursts without even reaching the filament state. So you can see the two. It can be pretty disgusting for some of the movies that you can go and look in the supplementary file. It's interesting to look at it, where even in between the teeth, you can have some airflow.
Yeah.
And it's really weird. So it's a complex airflow when you have this sound. Now we didn't look at the fricative, the S and the T's in detail. And I'm sure there are other type of sounds that I don't even know that are not all occlusive that maybe also produce droplets. And here we go back to the question about the linguistic. Here maybe talking about phoneticists, you say in English, and linguists will be very important to be more organized in the research.
Yeah. So delighted you actually, tongues, lips, and teeth enter your talk. These are solids.
Yes. Soft one.
Jesus, it's not even solid.
So
not even soft.
Zhiyang, there is a very interesting, for example, question that you could ask, and maybe this is the good community. When you press your lips and you detach them, when there is no saliva, it's very hurting. And when there is this tiny amount of saliva, the opening is very fast, but it is controlled by the de-wetting of the film. So there is a fracture, and it's the fracture of the saliva film in between the lips. Again, an interesting fracture problem.
Thank you. We should talk. Yeah. All right. Any more discussions? This is a really informal discussion because everything is on YouTube video. As a matter of fact, because these saliva thing, video, beautiful video about the disgusting event are recorded. Thank you.
You're welcome. But that's life. That's why life is with fluid and sounds.
Thank you. All right. Should we close?
Yeah, I think you should because there's no more other questions. So thank you again for listening, for everyone.
Beautiful.
For the nice questions.
Yeah.
Merci beaucoup. Yeah. Thank you.
De rien.
Merci.
And bye.